Hey guys, I hope you're doing well. I hope you're staying warm. Um, I am recording this Saturday night, so tomorrow's Valentine's Day, and y'all are my favorites, so of course I got you all done first. So I'm going to go over the the notes for the week, the assignments for the week. This will be posted on Edpuzzle, which is where you should be watching this at. And there'll also be a grade for watching the Edpuzzle all the way through. If you only watch 10 or 20% of it, it shows me. If you watch 99% of it, it shows me. So just let that show up as 100% and be an easy, quick grade for you there. They're saying that the snow is supposed to start tonight around 3 a.m. and basically not stop till late Monday. So, and then the wind chills are supposed to be stupid cold, well, pretty much for the rest of the week. So I'm going to be surprised if we go back to school this week. We do have a virtual Friday, so don't forget to send your attendance emails for Tuesday, Wednesday, Thursday, and Friday because it is a virtual Friday, even though at this point, by the end of this week, we will have been virtual for a month. So I miss you guys. I was looking forward to getting back into the swing of things after everything that's went on. But apparently we get another week at home. So here we go. I'm going to share my screen so you can see the slideshow. The slideshow is posted on Google Classroom. You should know how to find that by now. So, all right, I'm now screen sharing. So here we go. Your keynote or the slideshow that I posted starts with this white slide that tells you basically if you want to break this work up into a Tuesday, Wednesday, Thursday, Friday kind of deal. Here's what you're going to do. Tuesday, watch the lecture on Edpuzzle. That's this. So I'll tell you like where the stopping points are. If you just want to do each day's worth of work and stop, that's fine. When you go back to Edpuzzle, you can start it and watch it, for the next part of the day until I say, stop for Wednesday, and do it that way. Or you can watch the whole thing. It's completely up to you. Self-paced, okay? Just get it done by Friday, 3:30. So, Tuesday and Wednesday, watch the part of the notes that I'm going over on Edpuzzle, and there will be a quiz on Google Classroom that corresponds with that day's notes. So when I start with Tuesday, you're going to take a quiz that's called 216, which is the date for Tuesday, and that will be a quiz over that day's worth of notes. Same thing for Wednesday. On Thursday, you have an Edpuzzle assignment over Newton's laws. It is a Mythbusters. It's a really cool one where they make a giant Newton's cradle, which is the thing I have back behind my desk with the 5 balls that hit each other back and forth. So they make them bigger and bigger and bigger to bust a myth. And then Friday, there's USA test prep over Newton's laws. I think 3 of them are videos, and I think there's like 10 or 11 total, and they're not big and long. It shouldn't be more than like 30 minutes of work, maybe, if even that. So I don't think it should be too bad. Next week when we come back, we'll basically be reviewing the Newton's laws stuff, and y'all took that pre-test. It may be almost time for post-test. So we've pretty much done a whole unit on online at this point. So okay, so I am going to start with the notes for Tuesday. So last week I had you guys watching kind of a lot of videos and stuff like that over Newton's laws. You did a little slide assignment over Isaac Newton and what each law was. So I know that you have been well introduced to what Newton's laws of motion are. So for today, we're going to cover his first law of motion. But before we get into the laws of motion, I want you to understand a couple things that you're going to hear me say. So if I refer to something as a Newton, so such as 4 newtons, that is a SI unit measurement for force. So because Newton was the guy who kind of discovered force and gravity and how it all worked, when they needed a unit to describe force, they named it the Newton. Okay, so you might say it's got 4 newtons of force, pushing on it or something to that effect. So that is a Newton, the standard international unit for force. And we're going to look at what force is. If you're using it in a math equation, and there will be a little bit of math, it's going to be labeled F, and that's the push or pull one object exerts on another. So it's measured in newtons. And basically, a newton is like how far you can push, how much force it takes to push something 1 meter per second But it's just a newton. Just call it a newton. It's all good. Forces can cause a change in an object's motion. If a baseball's headed towards me and I hit it with the force of a bat, it's then going to change motion, right? It's going to change direction. Its speed's going to change. Its velocity is going to change. Changes everything. And also, more than one force can be exerted on an object at one time. Right now, I'm sitting in my desk chair, so I have gravity pushing me down, and I have the force of the chair pushing me up. Also, my desk is helping hold me up here just a little bit. So my arm is pushing down on the desk, but the desk is pushing up on me. So there's multiple different forces in play all at once. When you combine all of the forces acting on an object, that's called a net force. So if you look at this slide, you're going to see in purple here, net force. The combining of forces when two or more forces act on an object. So let's look at my books. So this is going to assume that the force from the top and the bottom are the same. So gravity is pushing it down and whatever it's sitting on is pushing it up. So those are equal. Now we're going to look at the left and the right. So we have, on the left, we have 2 newtons of force pushing it to the right. We have 5 newtons of force pushing it to the left. Which one of those is greater? The 5 is. So if I wanted to know the net force on this object, I would say it's 3 newtons to the left. How'd I get 3? The 2 newtons of force that are pushing right are going to cancel out 2 newtons of force that are pushing left. And that's going to leave us with 3 newtons left over. So think of it again. I have 2 going this way, 5 going this way. This one's got more. So the 2's are going to cancel. I'm going to end up with 3 newtons overall, and they're pushing to the left. So I'm going to label that 3 newtons to the left. If I had 5 newtons pushing down and 2 newtons pushing up, I would say I have 3 newtons down or to the right or to the left or whichever way the extra is going. So if I have my water bottle here and I have 5 newtons of force here, 2 newtons of force here, my 5 newtons of force is greater, it's going to push this 3 newtons to the left with 3 newtons of force to the left. Now, sometimes those forces are balanced. If they're balanced, you have the same amount of force on both sides. So they're equal in size and opposite direction. So on my books here, I have 4 newtons to the left, 4 newtons to the right. They cancel each other out. My books don't move. I have a net force of 0 newtons. Okay, so that's even forces on all sides. Again, unbalanced forces, just like the first slide with the books, okay, they're not equal in size and opposite direction. So net force causes that object to move in the direction of the force. So let's see here. With these books, I have 3 newtons pushing left, and I have 7 newtons pushing to the right, and I have 2 newtons pushing to the right. So I have 2 different forces being applied pushing these books to the right. So I cancel that out. So I'm going to take 3 away from the force on the left. So 9 minus 3 is 6 newtons to the right. So I'm going to add up my forces that are pushing the same direction. So on the left arrows, I have 9 newtons pushing right. I have 3 newtons pushing left. Those 3's cancel out. 9 minus 3 is 6 newtons to the right. All right, Newton's first law of motion. You should already have at least done a little bit of research on this, but an object will move at a constant velocity until a net force acts on it. So the way you guys have probably heard this described before, Newton's law is typically stated as an object in motion stays in motion, and an object at rest stays at rest. I'm sure you've probably heard that. Then there's going to be a little, asterisk by it that says unless a force acts on it. So an object in motion will stay in motion unless acted on by another force. An object at rest will stay at rest unless acted on by another force. I have my water bottle here. It's sitting here. It's at rest. It's going to stay in rest until I push it. Then it falls. Me pushing it was the outside force. Okay. I've got a car going 50 miles per hour headed towards a brick wall. It's in motion and it's going to stay in motion until it's acted upon by an outside force. Either it hits the brick wall, that's an outside force that stops it. You press the brake, that's an outside force that's going to apply pressure to the brakes and stop the car. So let's look at this a little bit further here. Newton's first law is also called the law of inertia, which is the tendency of an object to resist a change in motion. Okay, so the more mass an object has, the more inertia it has. So to resist a change in motion. So let's think of it this way. I have two boulders. One of them weighs 5 pounds. One of them weighs 50 pounds. The amount of force it's going to take for me to roll those boulders is going to be much greater on that 50-pound boulder than on the 5-pound boulder. The 50-pound boulder has more mass, therefore it has more inertia or resistance to change in motion. So if it's at rest and I'm going to push it to move it, to start it in motion, the resistance there until it starts moving is its inertia. So you guys also have probably experienced inertia in a car. So if you if someone slams on the brakes and your body flies forward, it's because your body is still in motion. Your body is kind of separate from the car itself. You're attached to the car, but your body's in motion. So if you slam on the brakes, your body continues moving forward, even though the vehicle is not, and that movement, okay? That's why you wear your seatbelt, but that's inertia. Also, that's showing you that your body is staying in motion until acted upon by the outside force. So if you don't have a seatbelt on, you apply that force, applying the brake, and then you fly forward because there's nothing holding you there. There's nothing, you're staying in motion until acted upon by an outside force. So you're going to fly forward until your body stops its motion as well. So what kind of forces can change an object's motion? Friction. So you guys should be pretty familiar with what friction is. So that's when two objects are in contact with one another. So like this, okay? This is friction. Air resistance. So that is the resistance an object has when it falls through air. Okay, so air is a force. Air is going to kind of create, it's basically air friction, okay? And then we have gravity. Okay, so that's the attraction two objects have on another. So gravity pushes things together or pulls things together or pushes things apart. And those different things can affect an object's motion. We're going to look at friction again here. Rougher surface has the greater friction. Which one's going to have more friction? A piece of copy paper or a piece of sandpaper? The sandpaper is going to slow things down quicker because it has a rougher surface. Okay. The more surface area something has, okay, the greater the friction. So if I have a marble rolling down a hill or I have a boulder rolling down the hill, the boulder is going to generate more friction because there's more surface area touching with the two objects, the dirt and the boulder. Air resistance, like I explained it a minute ago, it's basically air friction. It's also referred to as drag. If you are a fan of any sort of car racing or something like that, you may hear the word drag. So air resistance is determined by speed, size, and shape. So the faster something goes, the more air resistance it's going to deal with. The larger something is, the more air resistance it's going to have. And the shape, and this is where you get aerodynamics, okay? So the flatter something is, the greater the resistance. So if I'm flying a brick, okay, if I'm flying something, you know, rectangular shaped through the air versus something, you know, airplane shaped, the brick is going to have much greater air resistance. And that's why we have all these engineers dedicated to figuring out the best shape of things for air to flow over things. And you see that with not only airplanes, but even like in NASCAR, they put these cars in wind tunnels and blow smoke through the wind, and they watch how the air flows across the body of that car. Spoilers on the back of the car are literally designed for the air to push down on it to help keep the car down on the road. the law of universal gravitation. I'm probably not going to ask you that exact, like, what is the law of universal gravitation? But I want you to understand that the greater the mass, the greater the gravitational attraction, or the closer things they are together, the greater the gravitational attraction. So let's look. Actually, the first set of dots, they're the same size, okay? And so they have the same amount of attraction towards each other. You go to the second one down, your ball on the right is going to have the greater gravitational attraction. If you look at the third one down, those guys are the same size. Also, the fourth one down, they're the same size. But if I compare those last two, which one would have the greater gravitational attraction would be the bottom ones. They're the same size, but they're closer together. So let's look. I have two identical water bottles, okay, and they're spaced equally apart. They both have the same amount of gravitational attraction on each other because they're the same size, same distance apart. Now, with that being said, let me find something here. I'm looking, hold on. Okay, so here's my water bottle. I have a tape dispenser. This is smaller than the other water bottle. So the two water bottles had greater gravitational pull. Okay, back to my water bottles. There is more gravity between the bottles here than there is here because the closer things are together, the more gravitational pull there is. And we can demonstrate this using our fingers. So I want you to try this at home. So you're going to take your fingers and you're going to get them as close as you can without them touching. Now, when you're here, it's really easy to keep them not touching. When you're here, it's not hard. But as you get closer and closer together, it becomes harder and harder to do because the gravitational pull gets stronger and stronger. Speaking of gravity, I need you to know this number. It's very important. Gravity has an acceleration of 9.8 meters per second squared. If you are free falling, you were falling at 9.8 meters per second squared. You're going to need that number to calculate force when we move on to the second law, okay? So 9.8 meters per second squared. That is the acceleration or the force that all things in free fall have. We call that terminal velocity, okay? So the force of gravity pulling you down in a free fall is terminal velocity. There's a point in free fall where you've reached the maximum speed you're going to reach and you're not going to get any faster than that. So you don't continue to speed up until you hit the ground. At some point, you're going to hit a constant speed and you will stay that speed, 9.8 meters per second squared, until you hit the ground. Okay? So that is the notes for today, for Tuesday. What you need to do for today is go on Google Classroom and find the quiz that's called 2/16 or February 16th. I think that one had 11 questions on it, and you're going to do that quiz. Now, when I say it's a quiz, it's really just to make sure you went through the notes. You're going to have a lot easier time answering those questions if you have the notes pulled up. I'll just leave it at that. If you're doing this on a day-by-day basis, you can stop the video now and start it back here for Wednesday. But I am going to go on to the notes for Wednesday as well. All right, Wednesday. So Tuesday's notes went over the first law of gravity: an object in motion stays in motion, an object at rest stays at rest. We talked about terminal velocity, which was 9.8 meters per second squared, and you're going to need that number. Don't forget that number. We talked about force and newtons and all those good things. So today we're going to cover the second and the third law because they kind of go hand in hand. And there's not as many new terms to introduce. So we just did one law yesterday because there's a lot of extra vocabulary kind of to introduce there. There's not as much vocabulary for this. There is a little bit of math, but it's not hard. So look at the second law of motion. So it says a net force acting on an object causes the object to accelerate in the direction of the net force. It doesn't really, it's kind of hard to break down. So let's look at it this way. Basically, the second law of motion says the greater the mass, the greater the force needed to move it. We already discussed this. Yesterday, we talked about the boulder, the 50-pound boulder versus the 5-pound boulder. Which one is going to require the greater force to move it? The bigger one. The greater the net force, the greater the acceleration. So if you look at my little ball with the croquet mallet there on the right, if I hit that ball with 2 newtons of force, it's going to go a certain distance. If I hit that ball with 10 newtons of force, it's going to go 5 times that distance. Okay, it's going to go further. So if you guys bowl, if anybody's been bowling, some people are stronger bowlers than others. I'm like a mediocre bowler at best, right? But my dad was really good. And the only reason he was good is because he would throw the ball with such force that I would always make the joke that the pins would just fall down because they were scared for the ball to hit them because he threw it so hard at them. Well, he was demonstrating Newton's second law of motion. He was able to accelerate this ball much harder because he had a lot more mass and put a lot more force behind the ball than I did. And so that's a good example of the second law of motion. Now we're going to look at it in mathematical terms. Force F equals m, which is your mass, times acceleration, a. Okay, so F equals ma. So if I am given 2 of these, I can find the other one. Every single one of you should be in algebra. You should know how to do these types of equations. So we're going to look here. You're pushing a friend on a sled. You push with a force of 40 newtons. There's my F. So if you look right here, I'm listing what I have. F equals 40 newtons. Your friend and the sled together have a mass of 80 kilograms. There's my M, 80 kilograms. Ignoring friction, what is the acceleration of your friend on the sled? So I have F equals ma right here, but I have my F and I have my m, and so I need to get my a separated. So how do I do that? I divide the sides by m, which gives me a equals f over m. So this is how I find acceleration. Acceleration equals force divided by mass. So I have my F is 40 newtons. I have my mass is 80 kilograms. I divide that out and my acceleration is 0.5 meters per second squared. Now you have a couple of those, one or two of them on the Google quiz for today, but you're simply plugging in those numbers. I think one of them deals with it like this and the other one deals with gravity. And that's what we're going to look at here. So weight is the force of gravity on an object. Okay, so what if I weigh 100 pounds on Earth? Okay, I'm going to weigh less on the moon because there's less gravity, and weight is the force of gravity on an object. My mass is the same. I haven't changed the amount, mass is the amount of matter that makes up something. So my mass is the same no matter where I go, but if there's different amounts of gravity pushing on me, then my weight is different depending on where I'm at. So weight's the force of gravity, but what is the force of gravity? 9.8 meters per second squared. That's why we need that number. So if I want to know the weight of a suitcase that has a mass of 42 kilograms, how am I going to find that? Well, force equals mass times acceleration. So let's look. I have my mass and my acceleration. What's my acceleration? 9.8 meters per second squared. Okay, if I am trying to find the force of an object that's just sitting there, the force for that object there is going to be, the acceleration is going to be gravity, 9.8 meters per second squared. So I have force equals mass times acceleration. Force equals 42 times 9.8. The force, okay, is 411.6 newtons. Okay, so the force, weight, the force of gravity on an object, therefore the F. Okay, weight is the F here. You see this? Because it's a force, you can always calculate weight using force equals mass times acceleration. Where am I at? Here I am. Okay, I just talked about this, weight and mass. So mass, the amount of matter in an object, weight, the force of gravity. So the further away I go from Earth, the less gravitational force I have pushing on me and the lower my weight is. But I still have the same amount of mass making me up. So weight is the push of the gravity on the mass of an object. Okay, so we have objects in motion stay in motion, objects at rest stay in rest. We have force equals mass times acceleration. Time for the third law. Every action has an equal and opposite reaction. This one's fun, also pretty easy. So when an object exerts a force on a second object, the second object exerts an equal force back in the opposite direction. So if we go all the way back to yesterday where we were talking about these unbalanced forces and balanced forces and things like that, okay, basically it's telling us that the forces need to be balanced unless there's something acting on it to make it unbalanced. So there'd have to be some sort of, you know, somebody swinging a hammer or something like that, some sort of force to go with it. So an example is when you jump on a trampoline, the trampoline exerts the same amount of force back on you, pushing you opposite the direction. So in our time together through all the sciences we've had together, we've talked about like law of conservation of matter, law of conservation of mass, law of conservation of energy, and they all say that whatever we're talking about, energy cannot be created or destroyed. Matter cannot be created or destroyed, right? It all cycles through and changes, but it's all been here. The law of conservation of momentum is no different, okay? So momentum, if you're looking at it in mathematical terms here, is symbolized with a lowercase p. I don't know why. It's lowercase p. So momentum equals mass times volume. Okay, sorry, not volume, velocity. The V is velocity, not volume. All right, so all moving objects have some sort of momentum, and momentum is what's transferred between collisions. So if you think of the Newton's cradle, so again, the thing with the balls that go back and forth, okay, I have momentum coming into it, hitting it, it transfers through and gives the ball on the end momentum to go up and out and up and out. So I don't believe I have any momentum mathematical questions on there, but if I give you a momentum question, I want you to be able to answer it. So here I have, what's the momentum of a car? The mass of 1,300 kilograms, traveling at a speed of 28 meters per second. So I have momentum, okay, equals mass times velocity. Here's my mass, here's my velocity, okay? And here is my momentum, 36,400 kilograms per meter per second. So just like in all my other law of conservation of blanks, it basically means momentum is not created or destroyed. It's only transferred. So I have one car running into the back, it has momentum, it runs into the back of another car, then pushes another car, okay? And maybe that momentum goes down into the ground through the tires or into a tree or something, but the momentum only changes and transfers where it's at. Okay, so that's the end of the Newton's Laws notes. So for today, for Wednesday, you have another Google quiz. It's labeled 217. It's not as many questions as yesterday's. So yesterday's, I think, was 11. I think today's like 8 or something like that. If you didn't figure it out yesterday, it's very, very handy to have the notes open when you take that quiz. If you're doing this day by day, here's where you would stop for Wednesday and go do that quiz. All right, I'm going to move on to Thursday quickly. Thursday, you have an ed puzzle. It's called Mythbusters Newton's Cradle. What's really fun about this one is they start with the small Newton's Cradle and make it bigger and bigger and bigger until they're basically using like these huge wrecking balls to see what they can get it to do. So it's a pretty interesting episode there. And there's a few questions that go along with it on ed puzzle. And for Friday, Your work is on USA Test Prep. It's all over Newton's laws, and it's not a whole bunch. It's maybe 9, and then there's 3 videos. So there's like 12 things, but out of the 12 things, some of that should go by really fast. I don't expect you to have a ton of trouble with it. You be classifying things, so it might give you like an example of something. You need to tell me if it goes with the first law, second law, or third law. So it might be handy to have the notes up. That will conclude your work for the week. I really hope to see you guys again soon. I'm starting to I miss you guys. So if you have any questions, just like a normal virtual day, you can email me, you can message me on Remind, or you can get on my Zoom. It does take me a couple seconds to get on. So when you get on my Zoom, I don't just leave it up because it just runs everything down. So if you get on my Zoom, in my Zoom room, I get an email. When I get the email, I click the link and it joins me to my Zoom room. So it takes me about a minute to 2 minutes to hop on once you join in the room. So just give me a couple minutes. Let me get logged in. I'm also going to be doing the pre-K stuff with the twins and dealing with all that too. So if I'm momentarily away from the computer, I'll get the email that you're on and I can come right back and get on. I hope you guys enjoy the snow. Have fun. Don't get too cold. Bye, guys. Oh, wait, I have to stop my share. Okay, now bye.